presentation here today, in essence, is about the fact that our society really is in the midst of what I would like to call a perfect storm. A perfect storm of, on the one hand, the ongoing information revolution with big data and the Internet of Things as most recent developments. And on the other hand, the largest energy transition in human history. And I will argue in this presentation that those two major transitions are completely interdependent. Take, for instance, Europe. Europe, as the rest of the world, completely dependent on the provisioning of energy, is in the midst of a transition where we see a very quick uptake of what we like to call green energy production, solar and wind mainly, and also a dramatic change in the way we are using energy, with electric transportation as a typical example. At the same time, we see a decrease in the production and consumption of more traditional energy, like mainly fossil fuel-based energy production. And actually this is great. I mean, being from the European Union, our ambition is to really reduce the greenhouse emissions, of course, to slow down global warming, but also from a geopolitical view, we would like to become less dependent on less stable regions in the world for our energy provisioning. We have very ambitious targets to reduce greenhouse gas emissions, but the challenge for a company like Alliander, and Alliander is a Dutch-German energy distribution company, is that as a company we are responsible for the continuity of energy provisioning to our customers. And considering the development that I just told you about, we are witnessing a very quick increase of the complexity of the energy system. Why is this? Well, it's quite simple actually, because if you look at the red line here in this graph here, this is more or less the disbalance in the system that we've seen in the past decades or so. And the blue line is an example of the disbalance in the system that we are witnessing today and in the coming years to come. We see, in other words, a quickly increasing disbalance between energy demand and supply. Why is this? Well, it's quite simple, because when it's a sunny and or windy day, then we have more energy production than energy consumption typically. While on the other hand, if people get home in the evening and start to recharge their electric cars, we see a huge peak in energy consumption. So typically, unfortunately, peaks in demand and supply are not very nicely aligned. So our challenge, being an energy distribution company, is to manage this increasingly complex energy system. Our major response to do this is the introduction of what we call the smart grid. The smart grid is about many things. It's, for instance, about introducing smart meters, installing smart meters in millions of households. It's allowing us to have a much more fine-grained, much more detailed insight into the actual energy consumption and also local energy production by, for instance, solar panels on rooftops, than we had in the old days before we had the smart grid. The smart grid is also, for instance, about introducing energy storage. We are doing experiments now with houses, installing large batteries in their, for instance, in the garage to store energy when there is more production than consumption. And then this helps us to balance this system of demand and supply. So there are many things going on in what we call the smart grid, but sort of the common theme in the smart grid is about connectivity. It's about digitizing all possible assets like cables, like transformers, like houses, like cars, etc., and then using that connectivity to collect data from sensors into our central systems. Our strategy is mainly what we call building the connected utility company. It's about, as I said, connecting to our assets that are out there. We have tens of thousands of kilometers of gas pipes, hundreds, thousands of kilometers of electricity cabling, and we are connecting to those assets to get a more real-time and much more detailed view into their status. It's also, and in essence, by the way, this is an example, basically, of the Internet of Things. But we also, not to forget, connecting to our employees through mobility, and we are also connecting to our customers and other partners like government agencies or other companies to share our data with. So in the middle of all those connectivity activities, if you like, there's this thing which we call connected data or connected big data, if you like. It's about our efforts to connect data from all possible sources, including, for instance, our own enterprise systems like our ERP, CRM, and SCM, and other three-letter acronym systems that we have. This is our traditional IT landscape, basically. But also bring this together with data from what was also known as our geographical information system. These are the systems in which we register the location and the connectivity of our assets. Finally, very important, new source of data in our case is what we call streaming data. Streaming data basically is about different types of real-time data coming in about, as I said, about the status of our assets and the grid, but also, for instance, about social media data. We are using social media data, or at least we are doing some pilot projects on that currently, to use, for instance, Twitter data to see if we can somehow have an early warning about outages that may occur. And the reason for that is that without smart meters, and some regions we still do not have smart meters, to be honest with you, there we are dependent on customers calling us and informing us that there is an outage. This is the old-fashioned way of doing things. Nowadays, however, an increasing number of customers are using their phones to inform their friends or family that there is an outage. And so typically they are much faster in tweeting that there is an outage than calling us that there is an outage. So that's why, as an example, we are using Twitter feeds to detect outages in our grid. Anyway, so this whole picture of bringing different sources of data together is still quite high level. So what I would like to do is take you through some examples that give you a little bit more concrete feeling of what we are doing in this area of big data and analytics. So the first example that I have included is about what we call load forecasting. It's about basically predicting the future needs of our customers. It's about collecting massive amounts of data, both from our sensor or smart grid environment, where we collect billions of data rows about the actual usage of our grid. But it's also about trying to predict the future. It's about predicting how quickly people will be driving electric cars. It's about predicting how quickly people will be installing solar panels on their roofs. And bringing all this technological, demographic, macroeconomic data together is a challenge, I can tell you that, because these different data sources, internal, but also very much external, all have different formats, different semantics, so it's a huge challenge to bring this all together. But that's what we do. And why? Well, because the combination of all this data allows us to predict to a certain accuracy what will be the required capacity in our electricity grid or in our gas grid in the future. And if you know that we are spending annually literally hundreds of millions of euros on increasing the capacity of our grid, then a better prediction of what exactly is needed is really allowing us to reduce our investments by multiple percents. So there's a huge business case behind this that really allows us to be much more precise in focusing our investments where they are needed and in avoiding investments where they are not needed. So this is, I guess, is maybe not technologically the most, let's say, exciting example of using big data and analytics, but from an economical point of view, this is, to us at least, is a very important example because it really saves us tens of millions of euros each year. So another example that I have brought with me to present to you is this one. It's more tactical, if you like. It's about risk-driven planning of our inspection and maintenance activities. What you see here on the screen is part of downtown Amsterdam. And in Amsterdam, like any other city in the Netherlands and Germany, we have a lot of gas piping, underground gas piping, delivering gas to individual houses and buildings. And especially in older cities, these gas pipes sometimes date back into the 1920s and 1930s, so almost 100 years old. And these gas pipes, especially the older ones, tend to degrade. And in some cases even, they tend to leak, which is obviously, in the case of gas, is extremely dangerous. So we want to make sure that we focus our inspection to detect any leakages in our gas piping as good as possible. So in this example, what you see here is a map of part of downtown Amsterdam, and the blue lines are gas pipes that meet certain criteria. I won't go into the details, but I can tell you that these gas pipes are both made from a certain material that are, it's gray cast iron, in case you're interested, which is, let's say, quite a material that is not the safest material, let's put it that way. But then you also have the orange lines, and these are the contours of buildings that are within 1 or 3 meters distance from the gas pipes made of gray cast iron. So, to cut a long story short, this map tells us where to focus our inspection. It tells us where specific gas pipes are too close to buildings, and those are the areas where we really need to go first to see if there is any risk involved. So this is very important. So why is this interesting? Well, you know, the thing is that in the old days, before we had this system that you see here, we had an old-fashioned system that literally took analysts hours to complete queries, because this, believe it or not, is a highly complex so-called geospatial query. And in the old days, we had a system that if we were to run a query that met those criteria, it literally took hours to complete. Nowadays, we have new in-memory technology that allows us to run the same query in a matter of mere seconds. So this is really allowing our analysts to do a much more interactive analysis, doing what-if analysis, and really allowing us to pinpoint in a much more interactive way where we should focus our inspection and maintenance work. So a third example, which is actually more advanced than the two that I showed you before, is about what we call real-time asset condition monitoring. Again, you see a map on the screen. It's a neighborhood in the famous town of Zaltbommel. I don't expect you to be familiar with this town, but if you are in the Netherlands, I can recommend you to visit this town because it's a very nice medieval type of town where we have a neighborhood, in this case, where people, like elsewhere in our countries, are installing solar panels on their rooftops. And when people do this, this is registered into a database, and the contents of the database are projected on the map here. The little Z's here that you see are houses that have solar panels installed on their rooftops. This is not very exciting by itself, but what makes it more interesting is that you also see the little dots here, the little green, orange, and yellow colored dots. Those are in layman's terms, are transformers converting energy, electricity from medium voltage to low voltage. And the color that you see here on this map tells you something. At least this screen, by the way, is used by operators in the control room, and the colors of those circles give them an indication what is the current load on the transformer. If it's green, it's okay. If it's red, something needs to be done because the transformer is about to overload. So something needs to be done. So how does that relate to solar energy? Well, as I told you in my introduction, the production of solar energy is inherently unpredictable. When there is a cloud deck, there is less solar energy being produced than when it's a sunny day, right? And we live in a country when it's not like here that there are mainly blue skies. We live in a country when there is, 1 minute there is a cloud deck, another minute it's completely empty, right? So it's changing very rapidly. So that's why in this application we also have a live data stream coming from our Weather Institute that gives us detailed data about the cloud deck. Not just now, but the cloud deck expected in the near future at that very location. So this gives us information about the expected solar energy production in the near future. And then when we combine this data with, for instance, the time of day, because people tend to leave and go to their office, go to their job, or when they get home, they start to recharge their electric cars, for instance. So this all this data brought together gives us a picture about the expected energy demand and supply in the near future, which is then used by our controllers in control room to see whether action is required, whether transformers are still in the safe zone, or maybe some transformers may become overloaded in the next hour or so. And if that's the case, then the human operator in the control room, for instance, can do some switch settings and sort of load the system in different ways, so the load is balanced in such a way that no single transformer gets overloaded. That's very technical, so I won't go into there too much now. But this is still an example where we have a human operator in the value chain. So it displays information, it analyzes data in a highly automated manner, but still we have the human controller that is needed to take, not just to understand what's going on, but also to take corrective measures to prevent the actual overload from happening. So the final example that I have included is about, it's still, I must say, in research phase, but this is about taking away the human factor altogether. It's about a fully automated, what we call self-managing or self-managing energy grid. It's about a system, a large distributed system, where we have basically the Internet of Things, but in this case focused on the energy system, where we have a fully digitized system that is collecting data all the time, trying to understand the current status of the grid, and then if there is an outage, or if there is, for instance, if there is a cable broken somewhere, by whatever reason, by a digging damage, or by, for instance, about if there is a storm or whatever, if there is a disturbance in the system, this self-healing grid will be able to detect this automatically, and then, importantly, also take corrective measures automatically. So this system is not just about collecting data through sensors, it's also about the capability of a system to change the system through connected, what we call actuators. Actuators that allow the system to remotely change switch settings, so in case, for instance, if there is a disturbance, the grid can sort of reconfigure itself to limit the scope or the impact of the incident that was occurring. So in a sense, it's a self-healing, self-repairing grid that we envision here. And actually we have experiments in, although at the moment at very local scale, of actually doing this. It's also not just about, let's say, the technical continuity of the system. It's also about, for instance, to give you another example of the usage of the system, about allowing local communities to share energy with each other. It's about what we call microgrids, meaning that if I'm a house owner and I have solar panels on my roof, perhaps if it's a sunny day, I'm producing more energy than I can use because I'm away or because I'm not using that much energy at that moment. But this system then allows me automatically to signal the system that I have more energy that I'm needing at the moment. And then there is this sort of local marketplace or sharing economy, local sharing economy if you like, where I can sort of offer my energy surplus to the local market, and then other people or other houses or buildings that are in need of or have a deficit of energy may use my surplus of energy. So this is the future that we are working on. Anyway, so underneath all these examples is what we call our big data and analytics platform. I won't go into all the details because I don't have the time, but it's basically also very much like the value chain that Irfan was describing in his earlier presentation today. It's about collecting data from a whole myriad of source systems and then bringing all this data together in what we call a data layer. Different, let's say, more traditional data warehouses like Business Warehouse or our own Oracle data warehouse, but also containing what we call a big data lake, which is basically a large store, a very scalable data store where we can bring together all sorts of streaming data, like weather data or grid data, sensor data, etc. And then all this data is brought together in what we call a data provisioning layer, which is basically an access point to a whole myriad of underlying data sources. And then in the top we have, I think the battery of my pointer is running low, talking about energy. But anyway, so on top we see different applications, analytical applications that make use of the data that is provisioning through this data provisioning layer. This is a high-level overview of our current landscape that we are using as a platform to support this whole diversity of analytical applications that we have been developing. A few years ago, we started out with, let's say, siloed projects, with each project having its own technology stack, but we quickly found out that if we were to continue that we would end up with a IT landscape that would consist of tens or perhaps even hundreds of different silos that would be highly inefficient, obviously. So that's why a few years ago we decided to build this platform. And here are some of the technology that we're using. We're using HANA for the data provisioning layer for Business Warehouse. We're using Oracle for different databases. And on top we are using different business intelligence and analytical tooling to actually generate the intelligence that is coming from the data that we are collecting. Since 2 years now, we have centralized, well, not really centralized, but we like to call it federated, our people in the organization that are working on this. So it's about IT people, very well versed in collecting and integrating data, a very large part of any analytical project. It's really the collecting and integration of data is really the proverbial iceberg underwater. It seems simple, but there's a lot of work in that. But then also we have people working in these multidisciplinary teams with data science skills. So this typically are PhD level people with statistical, mathematical skills. And then as a third important element in these multidisciplinary teams, we have business experts, making sure that whatever the IT people and data science people are doing is actually aligned, obviously, with real business needs and is actually really, after they've done their thing, is really being implemented into the business processes. We are using a best practice called CRISP. It's a process standards that tells you how any analytical process is built up from different activities and different phases. And then also we have this enterprise-wide portfolio and governance structure, where we also, and I would like to stress this, allow different projects to be, let's say, more innovative. So we are working together with universities and other research institutes to actually build new types of analytical applications. But then after that, we are transforming those more innovative projects into real-world, business-enabled applications. So our top 5 success factors, if you're interested, it's about data science skills, which are quite rare. It's about data quality, obviously. If your quality is not well enough, then well, you're going nowhere with your analytical efforts. It's about awareness, about possibilities. It's about integration challenges, and it's also very much about making sure that it's not just IT, it's not just the data scientist, it's about multidisciplinary teams. So actually we just started on our journey. We have the examples that I've shown you are just, well, a few of many analytical applications that we have been developing, and we have a long wish list of new analytical applications for the coming years to come. For instance, one just to mention one, because it would take ages for you to discuss all the examples that I've shown here. But one is interesting, I guess, is fraud detection. It's about our capability of detecting energy theft, which is a huge challenge. And it's also an example where we bring our data together, as far as we are allowed, by the way, bring our data together with data from law enforcement agencies, so we can really pinpoint areas where people are not paying for their energy. Anyway, so, and there's a huge business case behind it. That's why I'm mentioning it. And it's also quite challenging in terms of data collection and analytical skills that are required there. Anyway, so thank you for your attention.